Thank you so much for inviting me, and I'm sorry for deviating a little bit from the title and abstract I sent in a couple months ago. Things have happened. So I'm going to tell you about SumofSquares for average case dispairs. And a silly rhyme apart, this talk is going to be focused on average case problems, which are problems where we are focused on understanding the computational complexity of solving a typical instance, as against understanding the complexity of solving a worst case instance. And typicality usually refers to some natural distribution, like probability distribution over instances of the problem. And what I'm going to discuss today is an algorithmic technique which has enjoyed like a fair bit of success in making progress on some basic average case problems. So my goal is to somehow convince you of the context and the utility of this technique and how in some sense you analyze it, and show you a glimpse of how some hopefully interesting problems to you can be solved using these ideas. So the insights in this talk are based on joint works with a number of people, and I will be somewhat relaxed about giving you the right references at various points, unless I'm mentioning a real theorem. If you are interested in finding out more, please ask me after the talk. Okay, great. So I want to start with a completely made-up anecdote. So we have a biologist, and they have collected some experimental data, and they are interested in analyzing this data for making some discoveries. You go and contact the resident computer scientist at the university. You say, well, I have data, I want to learn something about it. And let's say, for example, that the data is about the various features of crabs on some island or something, okay? And for some reason, the biologist has a hunch that, there are various different species of crabs found on this island. So the features collected belong to like different species. And what they would like to do is, separate out the species from this data, okay? So, of course, many of you, just like our computer scientists, realize that this is a problem called as clustering. So they say, well, okay, you are in luck. This is a problem that we very well understand. It's called clustering. So what do you want to do about it? And the biologist says, give me an algorithm to do it. And computer scientist says, well, in general, this problem is hard, so I don't know about it. And, this computer scientist might be living under a rock or something, but, jokes apart, this particular question of whether worst case hardness or computational complexity affects our ability to do machine learning is sort of, a question of both philosophical and practical importance. So I want to point out this recent talk that Sanjeev Arora gave as a public lecture at Simons Institute. And if you're aware of this law of clickbait titles, then you know the answer to the question. And just to be non-controversial, I would at least want to say that we have reasonable evidence to say that worst case computational complexity, like worst case hardness of various problems, in general does not tell us a whole lot about whether a certain machine learning task is possible or not. Okay? And the reason is not really that hard to understand. We don't expect data to really actively conspire against us. So even though we are really adept at proving lower bounds in computational complexity, in fact some of them are based on really clever, sophisticated mathematics. Many of them usually will not have a lot of relevance to a certain machine learning task. Okay. So what do we do? Well, So what we do is one of the part of the title today. So we study average case problems or average case models. So in the context of machine learning, a very popular approach to sort of deal with the problem, such as the one that the biologist brought towards us today, is to think of that the data itself is generated according to certain generative model. So you impose some assumption that the data was generated according to some idealized model. This model is usually probabilistic. So in some sense, the probability sort of gives you a lot of expressive power. In some sense, a lot of the features that you don't sort of want to enforce as parameters can be just done away with by saying that there are uncertainties that come out of just sampling procedures. Okay? So what you do roughly is basically you choose a probabilistic generative model, and then somehow the parameters of this model encode the structure that you want to recover. You don't obviously know these parameters. And what you want to do is look at the data and apply some algorithm to recover these parameters. Okay? So in the made-up story that I've been telling you, we can, for example, choose this pretty idealized and simple model called as mixtures of Gaussians. So, you imagine that there are, let's say, k different species of crabs, and each of these species has some average features. It is described by some vector, let's say mu1, mu2, mu_k. And you imagine that the data that the biologist collected was generated as follows. You chose, let's say, a species at random, uniformly. Then, to derive the feature vector of a certain crab that the biologist, saw on this island, you just draw a point from the Gaussian distribution with identity covariance and mean mu I. Okay? So this model is called mixtures of Gaussians. The details are not super relevant at this point because I'm still in my story. But the goal is that you look at IID samples generated according to this probabilistic model, and you want to somehow recover this mu1 through mu_k. Okay? So well, the computer scientist obviously knows all of this. So he says, I feel like mixtures of Gaussians is a great model for your data, and I also happen to know a great algorithm for it. And because this algorithm we are going to study a whole lot, in the later parts of the talk, let me actually introduce, some key aspects of it. So this algorithm is based on what are called as moments of data, and you saw a couple examples already in Piyush's talk. So if you have some data generated according to some probability distribution, the first moment of the data is just the mean vector of the data. The second moment, we usually call the covariance that, it's basically, it encodes pairwise correlations, and for each pair, the expression is what Piyush already wrote down there on the board. But you can even think of higher moments, and higher moments are nothing but correlations of, basically some object that encodes correlations between all possible triples and, quadruples and so on, okay? So in some sense, you can think of moments as summaries of correlation structure, in the data. And what's sort of very nice is that looking at, the first few moments of the data actually gives you a lot of algorithmic power, okay? So in particular, if you look at, this example of mixtures of Gaussians model that we were thinking about before, then just looking at the third moments of data under some somewhat mild assumptions on this means mu1 through mu_k allows you to completely recover them, okay, by just looking at the third moments, okay? And this is not an isolated example. This is what is called as an example of method of moments. It has a history dating more than like 100 years now. And a lot of, these probabilistic generative models, like really popular generative models, can be figured out, can be learned using just looking at third or fourth order moments. Okay? All right. So, this computer scientist gives, this whole speech to the biologist. He says, I have a great algorithm. It's awesome. It works very well. And the biologist goes and runs it on, the data that they have. And, usually we would expect a happily ever after story, but that does not happen here. They discover an issue here. So what's the issue? Well, the issues could be multiple, but in general, they all can be summarized as saying, I don't really think that I have found a good answer, okay? And what's the rough way to find out if I have found a good answer? Well, you divide your data into two parts, and just run, this mixture of Gaussian or whatever algorithm on each of the parts separately. Now, if there was really some ground truth to discover, like really some species structure in the data, then what I learned from the two parts should be roughly related to each other. I mean, they could be different, but they cannot be too different. So suppose I recover something that looks completely different, then I know that, well, something has gone wrong. My model is not correct, my algorithm is not correct, things have just gone wrong. So that's what the biologist reports. The fit doesn't generalize. I don't think, I'm doing the right thing here. And the computer scientist says, well, a number of things could be wrong. I don't know. Maybe you don't have enough data. Maybe, some nice condition that the model required to be satisfied is not met. Maybe this Gaussian assumption that the clusters are, individually Gaussian is too idealistic and is not satisfied with your data. Maybe there are outliers in your data. I don't know. There are tons of things that could have gone wrong. Maybe that's why, it's not working for you. But the biologist, of course, doesn't care about, why it has gone wrong. They're just interested in finding out, well, is there a different algorithm or should I collect more data? What do I want? What should I do? And the computer scientist says, And that's for a good reason. The reason is that, typically the algorithmic techniques that we have aren't that easily adaptable to, new variants of the problem. So, in this back and forth with the biologists that the computer scientists had, we discovered some issues. They're like likely issues, 1, 2, 3, 4. We would really like to, take our algorithm and modify them to sort of fit these new problems. And hopefully, they would be able to solve these, extended versions of the problem too. But it turns out, for example, that the method of moments that we're talking about, and, many in general algorithmic techniques have this issue that they aren't very easily adaptable to these new kind of situations, okay? Well, on the flip side, you could say that, well, maybe there is a fundamental impossibility here. But again, so I commented before that for worst case hardness, for like computational complexity theory, we are really good at proving lower bounds. In fact, we have developed several sophisticated methods to prove such lower bounds. For average case complexity, these kind of technology breaks. And the brief reason is that if you reduce one hard problem to another hard problem, you usually cannot save the distributions. Like you might create a hard instance of the problem you're looking at, but the distribution on the instances that you generate will not be the same that you care about. Anyway, so in some sense, it feels like we are nowhere. Neither can we say a lot about how to solve the variance of the problem, nor can we give a good reason about why we cannot solve them. Okay? So that's that's the sort of basic point that this talk is motivated from. And here is one way to attack or sort of make progress in the wake of this revelation. And in some sense, that's the approach I'm going to discuss today. So instead of like looking at all possible algorithms in the world and being creative with a particular, so usually what we do is like we take a problem and we be creative and think of an algorithm to solve it. I in fact want to discard that approach completely. I want to say that I want to fix an algorithm, okay? I'm never going to think of a different algorithm at all for this class of problems that I'm interested in. Whenever a problem comes in, I would apply just the same algorithm for that problem, okay? And still hope that I'm doing as good as any efficient algorithm could actually hope to do. Okay? If this is true, this is possible, it would be awesome. The less the amount of thinking that we have to do, the better it is. But moreover, we would also hope that even though so the first 2 points make this imagined fictional meta algorithm sound really powerful. The last 2 points, want at the same time that there be principled approaches to showing lower bounds for this meta algorithm, so that we can know when we cannot succeed and why we cannot succeed. And hopefully, in fact, the analysis of this algorithm is also easy to adapt, so that if we come up with a variant, we can just somehow, take our previous analysis, adjust it a little bit, and just continue working. So if all these 4 things, which look somewhat contradictory to each other, if all of those 4 things can actually be satisfied, we would be very, very happy. And this talk is about a promising candidate that tries to fulfill, these 4 pretty tall promises, which is the SumofSquares method. It was invented by a number of different researchers working in different contexts. And I won't go into the history today, but basically that's what this talk is about. Great. So that's the philosophy part of this talk. So what I'm going to tell you in the remaining time that I have is, so actually I plan on giving you, both these pieces of, both these pieces that I require for this algorithm before, that basically there will be some natural, broadly applicable way to, design algorithms using it. And at the same time, there'll be a broadly applicable way to prove lower bounds on this algorithm. But I won't have enough time, to go into both, so I'm going to actually just do one of them. I show it up here because, you can ask me questions at the end of this talk or whenever to, learn more about the second. So, this first part is going to be, so basically what I'm going to focus on now is tell you how you can design algorithms based on this method. And, if there is one take-home message I would want to impress upon you at the end of this talk is, the following sort of meta fact, which is that you can sort of design a machine learning algorithm in this approach in the following way. Whenever you have a simple enough proof of why small amount of data is enough to learn, like this is the kind of bounds we prove all the time in learning. Why are small number of samples enough for determining whatever we want to learn, So this approach will somehow take a simple proof of what is called as generalization bounds, this fact that small number of samples are enough to learn something, and somehow automatically convert it into an algorithm, okay? Of course, all the meat is in what simple means, so I'm going to hopefully come to that, later on in the talk. But, if you want to remember one thing, this is what you should take home, that somehow there is an approach that takes a proof of generalization, which is simple enough, and just automatically spits out an algorithm, okay, which is going to be efficient. So to illustrate this, technique, I'm going to take this example of the problem of outlier robust method of moments. That's the reason I introduced some of the elements before. Let's see what that is. So, so the algorithmic problem I'm interested in at present is actually very simple. Let's say I have, IID samples from some distribution, and I know that my distribution comes from some family of distributions, okay? So in the example that we saw, all possible mixtures of Gaussian distributions for each possible values of mu1 up to mu k is a family of distributions that I care about, let's say. That is what I will call my model. I get IID samples from this model, and I want to estimate low-order moments of this distribution. So let's say third moments. And of course, this is a trivial problem. What we will do is just take enough samples and take the empirical moments, meaning just like take the moments of the data that we see. And we know that if we take enough samples, then with high probability, this estimated empirical moment tensor would be close to the true moments. Right? Great. And then, even though it is like super simple, it's a basic primitive, in what is called as unsupervised learning. In particular, I already showed you that just estimating third moments gives you ways to recover, let's say, the Malicious of Gaussian model. Okay? So the twist I want to look at now is, this sort of issue that we are trying to assume that the data that we get is perfectly IID from the model that we've assumed. Okay? So in particular, what happens if the data that my algorithm gets is not perfectly IID, but just approximately so? So for example, there could be some amount of noise in my data. Let's say some tiny fraction of the samples that I see were corrupted somehow. So it's still pretty close to being an IID sample, but I don't have the promise of it being a perfectly IID sample. What happens to my simple empirical estimator, and how do I sort of, how do I accomplish this task of estimating the low order moments of, the distribution? So it turns out that this question was asked a long time ago by this famous statistician, John Tukey. And, so they came up with like a very concrete model for asking this question of what happens when you try to estimate moments from noisy data. So this is the model I'm going to be thinking about in the rest of the talk. So instead of an IID sample now, you get what is called as an epsilon corrupted sample. Okay? And what that means is roughly that, you took an IID sample, then an adversary got hold of this, sample that was generated. And the adversary somehow chose some epsilon fraction of the samples to his or her liking and changed them arbitrarily. Okay? So this model of noise is called malicious noise, that epsilon fraction of the samples can be modified, adversarially. And you get what is, the result of this adversarial corruption. And your goal is to somehow estimate the moments of the distribution that generated the IID sample, okay, before the adversarial corruption. So is the model clear? Yes? It's epsilon. So epsilon fraction, so there is no absolute bound on the number of samples that can be corrupted. There is a fractional bound. So, the percentage of samples that can be corrupted is bounded. It's at most epsilon. Magnitude of each corruption is unbounded. I can replace it by, infinite norm points if I like. Yes? Yeah, we'll come to that. So you're asking in some sense how general could my family of distributions be? Yeah, so in fact, one of the results that I'm going to explain today is going to be essentially all distributions, and I'll tell you what we can prove in that setting. So yes, we're going to come to that. Yes. Okay, great. So the first question we can ask, well, are we lucky? Just do empirical moments, the trusted estimator that we had before, does it continue to work? And actually not. Okay. In the sense that even if I had the ability to modify a single sample, I can somehow choose a single sample so far away from every other sample that the estimate that I get of the empirical moments would be very far off. In some sense, I can make it as far off as I want. And of course, this is silly because, if I corrupt exactly one sample, perhaps you will be able to notice it in some way. But the point is that, the basic estimator that I had, the empirical moments, is just a bad one. Okay? So in particular, if you try to apply the method of moments to learn, let's say, Malicious of Gaussians, with this silly estimator, you're going to fail arbitrarily badly. Okay, so you do need a different method, even if I introduce one outlier for that matter. Okay? Great. So this sort of inspired the whole literature on what is called as robust statistics. It's a sub-branch of statistics. It has been around since, Tukey asked such questions. The issue with these estimators that, people in statistics came up with is that they're typically, going to require time which is exponential in the dimension to compute. So if you have high dimensional data, this is going to be really expensive. Okay? So what we are really interested in is how do you, do this robust estimation? So how do you sort of, let's say, estimate low order moments from corrupted data and the running time should somehow be mildly dependent on the dimension. So it should at most be a polynomial factor in the dimension instead of an exponential factor. Okay, so that's our goal for today. So, again, in the interest of time, I'm not going to try to summarize. This is, by the way, a very recently developed and, in some sense, a very fast-growing area. Even though, in some sense, it is less than 2 years old. Just the topic of efficient, robust estimation. There are many, many papers. Perhaps 50 or so papers already on this topic. I'm not going to try to survey that. I'm just going to tell you one example, basic result. And sort of spend my time on that just to show you, illustrate, this technique that I'm interested in today. Okay? So, so let me explain this result that I'm going to talk about for the rest of the talk. And in some sense, it's the most basic result. And even though it's such a basic result, it requires somehow a sequence of 3 papers in order to get, in some sense, the right, in some sense, the right answer here, the right theorem. The theorem is the following. Suppose you get an epsilon corrupted sample from an arbitrary distribution with some covariance matrix sigma. And the covariance matrix is what is already, you saw in Piyush's talk, is basically, the pairwise correlations after centering with the mean. So say you get an epsilon corrupted sample. You don't really need to know sigma, but imagine that there is some parameter like that. Then in polynomial time and in polynomial samples, I'm going to be rough about this. So in some sense, you can ask me later about the precise bounds, but in polynomial time and polynomial samples, this algorithm recovers an estimate of the mean, okay, such that the distance, the Euclidean distance of the estimated mean from the true mean is going to be about square root of epsilon. Remember, the epsilon is a fraction of corruptions that you have, times the largest eigenvalue, square root of the largest eigenvalue of the covariance matrix sigma. Okay? And in some sense, okay, I mean, there's a simple example which proves that this dependence is optimal, but roughly why you can, the reason to expect this dependence on sigma to the 1/2 is just that, this largest eigenvalue of sigma sort of measures, is there a direction where the distribution has a huge variance? If the distribution has a huge variance, the adversary has sort of a larger space to introduce outliers and sort of try to fool you. So in some sense, if the distribution has high variance in some direction, the adversary can definitely make you, cause you to make larger errors. So if that doesn't make sense, just believe me that in some sense, this algorithm gets you this guarantee, and it also happens to be information theoretically optimal. If you make larger assumptions, this is sort of answering your question in some way. If you make better assumptions, let's say, in fact, if you make the other extreme assumption where the distribution was like a single Gaussian, it turns out you can better this result. This epsilon to the 1/2 can be replaced by just epsilon up to some log factors. But so I mean, we don't need to sort of care about these differences for the purpose of this talk. Okay? Right, the sigma to the 1/2 dependence is in some sense what you cannot do anything about. Really what we care about is what is the right dependence on the fraction of outliers, epsilon. Okay? Great. So in the recent work, we sort of, built on this various great papers that started this study of robust estimation. And instead of giving you a theorem statement, which would require me to spend about 15 minutes, I'm just going to tell you that, what we can do is we can work with weaker assumptions, which means we can work with distributions which are, in some sense, there is a way to quantify where you are in between an arbitrary distribution and Gaussian. And for every one of those ways to quantify, you get some result, and it turns out that that result is information theoretically optimal. But the more important fact is that the previous work sort of got only mean and covariance, but our technique sort of very naturally extends to higher moments. And the nice thing is that even if you get third or fourth moments, then you can directly apply method of moments and learn mixtures of Gaussians and all other models that I showed you before. Okay? So I'm not going to discuss the quantitative versions of this result. Instead, what I'm going to show you is just a different proof, and hopefully you will be convinced that it is a simple proof of the same theorem that I showed you before. Okay? Just this mean estimation, basically under no assumptions. Okay? And the nice part about this is that essentially all our proofs are not really more complicated than the proofs that I'm going to show you today. So really, if I tell you this and maybe we sit down together for 15 minutes or so, you'll be able to reconstruct every other proof in the paper. So it's like really simple. Great. So one thing I want to stress is that the algorithm in the end is going to be just some convex program, and you will just output whatever this convex program computes. So there is no outlier removal, no additional processing of data or anything. You just like run the program, whatever it returns is your answer, it's going to be accurate. Okay? All right, so I'm going to explain a proof of this theorem in the remaining part of my talk. How much time do I have? Okay, great. So if you haven't taken a class in learning, which I find impossible, then let me remind you that here are 2 steps that any learning class will teach you on how to do unsupervised learning, or even like, supervised learning for that matter. You show in first step what is called as identifiability. So unsupervised learning I think of as a problem of estimating hidden parameters of a distribution. Identifiability is a statement that says that looking at some small number of samples from the distribution uniquely identifies up to some tiny error these parameters that you are trying to learn. Okay? So in other words, it's a purely information theoretic fact. It says that what you're trying to learn, the information about that is actually present in some small number of samples with high probability. Okay? So, in some sense, identifiability is a necessary condition, like you must establish it somehow for any algorithm to work, efficient or not. In some sense, it can be thought of as the first step. And if you've proven any Rademacher complexity upper bounds, then this is that step where you're trying to show that some small number of samples are enough to identify whatever you're trying to learn. Okay? So in general, this only yields an inefficient algorithm. So what you do is you do prove identifiability. You somehow convince yourself that small number of samples are going to be enough. Then usually you stop and you go to the second step of algorithm design, where you try to construct an efficient algorithm for the parameter recovery problem that you care about. And in many cases, even though Piyush's talk is sort of a counterexample to what I'm going to propose, but in many cases, the first step is usually easy, like proving why a small number of samples is enough is usually not that hard. Coming up with an efficient algorithm can actually be quite non-trivial. Okay? So here is what the SumofSquares approach allows you to do. It basically allows you to cancel the second step out. In some sense, if you have a simple enough proof of identifiability, this is what I was telling you before. If you have a simple enough proof of identifiability, then in some sense, the second step is automatic. Okay? So I'm going to sort of show you this approach in action for this mean estimation problem that I showed you before. Great. So, of course, the important thing is the following. The whole meat, as we discussed, is in this word simple. What does a simple proof of identifiability actually mean? It will turn out that many natural proof strategies that we actually adopt, you'll see, in fact, one example very soon, actually already happen to be simple in the sense that we care about. So in some sense, in disguise, you probably have already shown many algorithms, you've already established that many algorithms are actually efficient, perhaps without knowing. Okay, great. So let's see why this is going to work for our example today. I just want to mention that there is a more general paradigm called as taking certain proofs and converting them into algorithms, which actually not only works for average case or machine learning problems, but also beyond for worst case problems. But again, I can discuss that offline. So this approach is basically a specialization of that approach to the problems in machine learning. Great. So let's try to understand why are small number of samples with an epsilon fraction of corruptions in them still enough to identify the mean within some small error. And the small, of course, is square root epsilon times 1/2 power of the largest eigenvalue of the covariance matrix. Okay? So let me first draw a diagram and tell you what's sort of going on here. So let's say this gray egg. So usually we'll have some class of distribution that we care about. Let's think of this gray egg thingy as the set of all n size samples, okay, from the distribution that we care about. Okay? And in some sense, you should imagine this to be the set of all typical samples that you can get from any distribution in the class of distributions you care about. Okay? So what you get is, some sample here. Okay? It was generated according to some model. Then some adversary took you, some adversary sort of, corrupted epsilon fraction of the samples and pushed you out to a point, this red point outside. Okay? The guarantee you have about this red point in relationship to this green point is that, the intersection of the points in the corrupted sample and the green sample is like 1 minus epsilon fraction of the total number of them. So their intersection is 1 minus epsilon times n. Okay? Now, you only get to look at this point. You don't, of course, know this green point. So in some sense, the only thing you can do is come up with, the nearest point in terms of Hamming distance inside this gray ball. And I'm not thinking of efficient algorithms at all here, okay? I'm just thinking of, what is the silliest algorithm, brute force kind of algorithm that you can hope to do here. What you can do is, I just get to look at this red point. It might actually be outside, the set of gray balls. So all I can try to do is, try to push it inside. Just try to find the closest possible point in Hamming distance, closest possible set of samples, in set of n samples in the Hamming distance, which does actually satisfy the property of being in, the class of distributions I care about. Okay, and I cannot do anything but return the mean of this blue guy. I really have no other information. So this is in some sense the optimal algorithm, if at all, it is efficient. Yes. Yeah. Yes. Yeah, and then I clearly cannot distinguish between zero corruptions and epsilon fraction of the corruptions. I really have no ability there to distinguish between the original sample and the corrupted sample, which still lies in the class of the distributions I care about. So there, in some sense, you identify a canonical case where mean is not identifiable. Right? Like in some sense, if the mean of these 2 points is far away, then what can we do? We cannot distinguish between those two cases at all, information theoretically. So in fact, this question already says what we require, from our class of distributions for this task actually to be possible. We would want that if there are 2 points in this gray ball, which are close by in Hamming distance, then their parameters should be close. Because if they are not, there is no way we can actually try to distinguish between them at all. Okay? Is it clear? Okay, great. So, if you've seen coding theory, then this is some analog, some approximate analog of unique decodability or whatever, but doesn't matter. This point is not important. So, this I guess is the same point I just made, that, robust estimation is possible only if somehow any epsilon corruption of the sample that you see leads you to and somehow if there are two distributions in your family which are close by, then they should have close by parameters. If this is not true, then, there is no way to do robust estimation. Great. So therefore, in some sense, what we are worried about now is why do nearby samples for the mean estimation problem actually have a close by parameters? Okay. So if I take two samples which are, let's say, epsilon close to each other in Hamming distance, why are their empirical means close by together? So let's write down the lemma and then try to prove it. So this lemma says the following. Say x and x prime are two sets of n samples, so n size samples, which intersect in epsilon fraction of the positions. So they are epsilon close in Hamming distance. And epsilon is like non-trivially away from 1, so it's not like too large. Then the distance between the estimated means from the two different samples, x and x prime here, is at most epsilon to the 1/2 times sigma x is the square root of the empirical covariance. Sigma x is the square root of the operator norm of the empirical covariance of the sample x, and sigma x prime the similar quantity for x prime. Is the statement of the identifiability lemma clear? I'll quickly show you why this is enough for the claim that we are shooting for. But is the statement clear? Is all the terms appearing here okay? Yes. Yes, mu is just the empirical estimator. Just let's take the empirical mean of the two samples x and x prime and trying to understand how far apart are these estimates. Okay? Great. So let me convince you that this establishes identifiability. Okay? So I'll give you an inefficient algorithm that uses this lemma to actually find a good estimate of the mean. Okay? Here's the inefficient algorithm. Find an epsilon close sample that is the smallest possible, largest eigenvalue of the covariance. So find me a sample which is, as close as possible to the sample that I actually see, and, which minimizes the operator norm of the covariance matrix. Okay? I already know that the true distribution, the true IID sample that I saw before, is a valid solution. Therefore, I know that. So if I try to find, so let's say I look at x prime and try to find some sample x, I know that sigma x cannot be more than sigma x prime. I guess I reverse the order here. The point is that, I know that there is a solution where the largest eigenvalue of the covariance matrix of the sample that I find is no more than the largest eigenvalue of the IID sample that I actually must have generated before. Okay? If that is true, then sigma x plus sigma x prime is at most 2 times the largest eigenvalue of the covariance matrix. So up to constant factors, I actually have what I wanted. Is this simple argument clear that this identifiability lemma implies an inefficient algorithm? So in particular, it tells me why I can identify the mean up to the square root epsilon times sigma to the 1/2 error. Okay, good, great. So now what I'm going to do is, give you a simple proof of this lemma. And if the proof is simple, then the point is that there is a convex relaxation of this trivial inefficient algorithm, which actually will work. In other words, like there is a simple way to, so in some sense, one way I could do is, come up with some creative way to relax this inefficient algorithm, this brute force algorithm, then try to analyze it. In this world, we just forget about this step. We actually do the reverse. We just try to prove this lemma in as simple a way as possible. And it turns out that the other job of coming up with an efficient algorithm will take care of itself automatically. Okay? So let me tell you a simple proof, and you'll see in some sense perhaps the most natural proof you could come up with. So since I want to bound the Euclidean norm of mu x minus mu x prime, I can try to upper bound the inner product with any vector u of mu x minus mu x prime. Okay? So I write mu x as 1 over n sum I xi and mu x prime as 1 over n sum I xi prime. So u inner product mu x minus mu x prime is equal to this left hand side quantity. Okay? So I'm going to just basically walk you through the proof and then ask me questions if you don't follow. So now I observe that xi and xi prime actually are equal for 1 minus epsilon fraction of the i's. So I try to sort of take advantage of that and write this 1 over n times sum over I. I basically write the indicator of whether xi equals xi prime. I know that if xi equals xi prime, that particular I, the term corresponding to that I contributes 0. So the only contributing terms are when xi not equal to xi prime. Okay? And then I have a contribution of u inner product xi minus xi prime. Okay? Now I use our favorite inequality in the world, the Cauchy-Schwarz inequality. This so I hope all of you know the Cauchy-Schwarz inequality. I'm just I have an expectation of some function f times some function g. This is at most square root of the expectation of the same function times square root of the expectation of the second function. Say that again. There is a square. You mean here? Here. Sorry, yes, you are right. Here should be, it should be a square here. Good, it means that at least one person is following. I have weaker standards of what following means. Yes. Yeah, absolutely, yes. So this is a square, sorry about the typo here. But the only observation now is the following. That sum over I of this indicator is epsilon n. Because you know that xi is not equal to xi prime in only epsilon positions. When I divide by 1 over n, I have epsilon coming up here. So this is epsilon to the 1/2, the first term. Okay? So I write this as epsilon to the 1/2. Now, in some sense, I only have control of the covariance matrix. So I somehow write everything in terms of centered random variables. So I subtract means, right? So I subtract means and write xi minus mu of x, xi prime minus mu of x prime. And then, I basically just control the term that I added and subtracted. Okay? Now, here's the point. There should be a square here that and a constant here. Sorry about this. But the point is that this first term is at most sigma x because it is nothing but, well, if it was written correctly, then it is the quadratic form of the covariance matrix of x. Similarly, the second term is going to be, the quadratic form of, the covariance matrix of x prime. So these two are the terms we actually like. The third term, I'm going to just write it like this because it's a constant. Remember that mu x minus mu x prime is a fixed vector. So, there is no summation that applies, summation or expectation that applies to this third term. So all I have now is, that this quantity that I care about on the LH, like left-hand side, is at most epsilon to the 1/2. The term that I care about, sigma x plus sigma x prime, plus something here, okay? And now the only observation is that, like this term is actually the same as what is inside here. This is nothing but u inner product mu x minus mu x prime. This is what we started with. So I just rearrange. I just subtract this term from the other side. Oh, sorry about that. So I get something like 1 minus epsilon to the 1/2 times the same term is at most epsilon to the 1/2 times sigma x plus sigma x prime. And if epsilon is not too large, then 1 minus epsilon to the 1/2 is at least some constant. Okay, you don't need to follow all the details here. I think at least if you roughly see how simple and how trivial things are, then I would be happy about this. Do you have any questions other than the typos already on the slide? Yes. Yes. Yes, and Prateek has already found out how to prove the in-between versions of the fact. If I assumed, let's say, bounded kth moments instead of just covariance, then I can use Holder's inequality. And instead of epsilon to the 1/2, I'll get epsilon to the 1 minus 1 over k. So I'll get actually a better dependence on epsilon. Yeah, it's the same proof. Basically, I've told you in some sense everything that's going to happen in this paper. This 3-line proof is in some sense all that's going to happen. Okay, and it turns out that there is sort of a magic box, which I'm going to discuss in the last 5 minutes. Hopefully I have 5 minutes, right? Ah, great, yes, great. So it turns out, so here is the lemma. It's not really a lemma, it's some meta lemma. There is a magic box that can actually mechanically convert proofs, as on the previous slide, the simple 3-line Cauchy-Schwarz-based proofs on the previous slide, into an algorithm, just mechanically. Okay? And we're going to study this mechanical box in a moment, but basically, the algorithm that comes out of the previous slide looks like this. I just wanted to show you how simple it is, so I wanted to write it down explicitly. If you've seen a quadratic program, before in your life, this is some simple quadratic program. My variables are, the new samples that I want to construct. So it really is the relaxation of that brute force program that I showed you before. Find me a sample which is epsilon close and minimizes the covariance. Okay? So I minimize the covariance matrix. I want to encode that x prime intersects x in 1 minus epsilon fraction of the position. So, these wi variables sort of, force me to do that. And, that's it. It's a trivial quadratic programming formulation of the brute force program that I showed you before. There is a sort of a mechanical way to take a quadratic program and convert it into what is called a semi-definite programming relaxation. It turns out that semi-definite programs can be solved efficiently. And in some sense, what we showed on the previous slide is an analysis of that semi-definite program. It's a proof that the output of the semi-definite program is actually going to be a good estimator of the mean. And in some sense, you don't have to do any of that. That's all a theorem, and it's there is a formal version of this lemma, basically, that you can just cite and be done. Okay, great. Yes. 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 So that such is actually what I'm going to discuss now. That such, or the simplicity of the proofs that I pointed out, actually comes from a fairly deep and very interesting theory of what are called as restricted proof systems. So these are called as SumofSquares proofs. And I'm going to be somewhat, wishy-washy in this part. So, this is just to sort of tell you what to look out for. If you don't follow, just ask me questions later, okay? So it turns out that, a SumofSquares proof is some way of reasoning about polynomial inequalities. So Cauchy-Schwarz actually can be thought of as some inequality about polynomials. That's a certain polynomial is always non-negative. There is a whole class of such inequalities. It turns out that there is a restricted proof system to prove such inequalities. So in general, we know mathematical proofs, but it turns out that there is a way to restrict the kind of proofs we can do. This class of proofs that we restrict to is called a SumofSquares proof. In some sense, these proofs are graded. So there is sort of a complexity measure of how complex the proof is. Okay? So this complexity measure is called the degree. It turns out that degree t proofs can be efficiently found in some exponential in t time. So if t is a constant, d is a dimension here by the way, then we'll have a polynomial time algorithm to find such a proof. Okay? So yeah? So in other words, you're asking about numerical accuracy issues? That's sort of the only issue here. It's a non-trivial issue, and yes. So what I'm saying in some sense is true with sort of a pinch or maybe a bucket of salt or something. But it's sort of useful enough that I want to sort of stick to this version. Yes. So in some sense, so here is one way to state it. Right. So it's not really about, I mean, even as like, it's not special about SOS. It's just like SDPs themselves, cannot be solved. Like all SDPs cannot be solved exactly in some sense. Right. The small. So in some sense, here is a more accurate statement. Suppose a certain polynomial inequality has a SumofSquares proof of the inequality, where the bit complexity of the proof is small, like press polynomial in all the parameters that appear. Then you can find it in polynomial time. Right. So this is a more accurate version. What's in some sense, when we establish the SumofSquares, in some sense we do the proofs explicitly. So we actually write down the steps. So in some sense we can also follow through the steps and find out the bit complexity. So in some sense, in all the arguments that we actually do to design algorithms, we explicitly also actually have to keep track of the bit complexity. In general, it's not going to be true. Small bit complexity, yeah. In some sense, it's a constraint that simple proofs also have to be, low in bit complexity, not just in degree. Great, but if that discussion, you can completely ignore, safely ignore for this, for the high level version of this talk. Basically, simple proofs can be found efficiently. There is some measure of simplicity. It turns out that many natural inequalities that we employ in our proofs, just like Holder's inequality that Prateek pointed out earlier, but along with many other inequalities, they all actually have simple proofs in this proof system. And that's why, in some sense, that's the more formal version of the claim I made before, that if you have a proof that only uses the simple inequalities about polynomials, then there is an efficient algorithmic version of it, and you don't even have to try to sort of get to it. It's just an automatic translation. Great, and okay, so that, and again, just to stress that point, this is not something you to do for the particular paper you're trying to write or particular problem you're trying to solve. This is something that is a ready-to-use general toolkit. You obviously have to perhaps, try to combine them together in some, some nice way for your particular application. But the point is that you don't have to start from scratch for getting this translation from, proofs to algorithms. Great. So I just want to impress you here that, the application I showed you is just one of many, many applications of, just the same paradigm. You can do a lot of, unsupervised machine learning with just the same trick of just doing an identifiability proof. And just letting the algorithm or this lemma, the magic lemma, do its job. Great. So that's sort of all I had to say. Many things I did not touch upon this talk, but is sort of related to the same topic. So quickly, one basic and one super important thing that I've not touched upon in this, in this talk is the application or understanding of the same technique. It's a powerful technique in some sense, even for worst case problems. And analyzing it in some sense for those problems is a big open question. Ask me later about that. There are more sort of vaguer open directions like, how do you sort of use this technique for understanding whether crypto assumptions are actually, solid? Like, do they hold or do they not hold? Similar, kind of questions can be asked about game theoretic questions, etc., etc. Yeah, ask me offline about any of these directions. Thank you.